What up, friends? Today we're going to learn about section 7.1, which is going to cover exponential growth functions. For the video today, you will need your notes, you will need a calculator, and then you'll need access to the course Canvas page. So that's where we're going to start today, is on the course Canvas page, because I just have that written on the top there. Exponential growth, what we're going to be studying, are just exponential functions, are fundamentally different than the things we've learned before. Now, we've encountered some exponential things, but we never really dive into why do we care and why is it different than things such as lines or like our quadratic functions. So I want you to start by watching this video that's linked there. If you don't watch this video, you will not fully learn today's lesson. So I just want to make sure that we understand this is a required portion of the video. Rather than me making this section, I thought this video was much better than I could ever do. And what it's going to compare here is it's going to compare the fundamental types of things we've seen before, and then what we're going to dive into is our exponential. So I want you to pay close attention to what they talk about: a linear function, which we know from Algebra 1, the quadratic function, which we also know from Algebra 1, and the exponential function, which is what we're going to really dive into in our course today. So I want you to watch out for the words like common ratio, common differences, and all those good things. So after you're done watching this one, then we're going to come back to our notes. So go ahead and pause my video and fully watch this one. And then what I've done here is I've summarized some of the main ideas that I would want to make sure that I have written down on paper when I come back and study this. And again, making sure that I would be clear that what I have on these little sticky notes here by no means covers all of the content in the video. I'm leaving that content to you and your responsibility, just to make sure that you understand it's your duty to watch that video. But just recall some of the main things about linear changes and functions. And what we are going to be doing, we're actually going to break our exponential study into 2 days: growth, getting bigger, and decay, getting smaller. So I'm just going to talk about lines that are growing or getting bigger. But all this holds true in general. But linear growth has that constant change, right? Meaning if we look at like a change in x, when I change x by 1, the change in y is always 3. And that's a main kind of big thing to look out for, is when we're talking about these patterns like constant addition or constant subtraction for linear functions. That pattern only works, of course, if the change in x is always the same. So like, for instance, if we looked at this table and for some crazy reason the next x value was 4.5 and the next y value was 13, even though we see the y value still increasing by 3, this wouldn't be a linear pattern then, because the x's didn't change by 1. They changed by a little more. And again, we see that not only in a table, but we can see that in a graph as well. And what we're looking at in the graph, and I just want to connect it because we see slope as that constant change, right? I'm saying if I started here on the line and I change my x's by 1, what are my y's changing by? How far up would I have to go? I have to go 3. And that pattern would always hold true. So if I go that same distance to the right, so notice how this blue segment is the same length as that one, to get back up to my line, it's going to be the same distance as it was before. So every time I move left and right by the same amount, I'm moving up and down by the same amount. And then we have our new function, or our new type of relationship, our exponential functions. And if we're talking about exponential growth today, rather than the change being constant, like here it's always going up 3, the growth is going to be changing. Now, we are going to see a pattern in our table, right? When we see an exponential function, we want to associate that with a multiplication pattern rather than an addition or subtraction pattern. But what we'll notice is the actual comparison of the output values isn't the same, right? The difference between 4 and 7 was 3. If I started at 7 and I got to 10, I increased by 3. Here, we'll notice there's a multiplication pattern, but the changes in y, which I'm just using as a delta or triangle y, here I added 2, but between the next two y values, I added 4. And the next time I would add something that's not 4, so on and so forth. And again, when we're talking about those patterns, of course, we are assuming that the change in x is always the same. Now on a graph, what we're noticing, as I said with this linear one, every time I went right that distance, my up and down distance was exactly the same. Now in a exponential pattern, look at my colors again here. If I go left and right the same distance, which is changing my x value by 1, do you notice how the purple lines are different lengths, right? This one is a little bit shorter than this one. And if I try that again, if I go left to right the same exact amount as I was before, sorry, Now I'll notice my purple line is going to be even taller to get back up to that graph. So we can see that the change in the outputs is changing. Now there's a pattern to how it's changing, but the actual values are different. Now, what we're going to start with today in example number 1, we're not going to do much of it. I'm actually just going to use it as, again, one more time to re-emphasize the concepts behind exponential growth. So I want to simplify this problem. It says Austin, Texas has a fast-growing city. I don't care about that little thing there, kind of confused me actually. Now, what we're going to say is rather than 2.5 growth, that's kind of hard to work with. Let's just start with 25%. It's easy to cut things into quarters. And instead of the population starting at a weird number like that, let's just make it 100,000. All right, so like what's going on with exponential growth? What I want you to see with this one and what you can draw with me is let's start with a little graph over here. And let's say this is going to be our years and this will be the population. So what they tell us is in 2013, the population is 100,000. So I'm just going to draw this vertical bar that represents 100,000 people. Just to make my iPad work a little bit nicer, I'm going to take a picture of it so it doesn't get erased. So this is the population in 2013. Now, what's going to be happening, the city is going to grow. And it tells us in the problem that it's going to grow annually. So every year, they will grow by 25% of the people they originally had. So in other words, in 2014, all the people that currently lived there or from in 2013 are still there, right? Because our population is growing, so nobody can move away. So that the population from 2013 still there, but what we're going to do now is we're gaining 25% more. So if this was the original population, I'm just cutting it into fourths and saying approximately this much is 25% of the population. So that much right there is how much we are going to grow by next year. So now we can see our population in 2014 is kind of made up of two groups of people. The people who are already there in 2013 and an additional 25% of the new people. So we can see now that we have more people in 2013, or excuse me, in 2014 than we do in 2013. Let's do it again. So in 2015, how many people are going to be there? What's this population going to look like? Same exact pattern will happen though. So if our population is growing, all the people that were originally there still have to be there, right? So I'm just trying to take a good picture of that. So we'll take all these people who lived there in 2014 and we'll make sure they still live there in 2015. But now what we are going to do is we're going to grow by 25% of the people that were there last year. So this is the entire population of last year. So I have to take this entire green rectangle and cut it in half and then in half again. So this section here now is how much we are going to be growing by. So 25% of last year. So I'm just going to copy that. I'm going to remove it so we can see the original. And then now this is how much we have grown by. So I want us to notice a few things, right? The original population of 2013, still there. They never moved away, right? The amount that we gained in 2013, these new people, were related to how many people lived there, and they never move away. But then what we notice is each year, we are gaining slightly more people because we're taking 25% of the people that were there last year. So let's compare these, right? The growth from this year is this purple rectangle. That's a lot of people. But the growth the next year is now this green rectangle. And if we compare those sizes, right, the growth isn't the same. There should be more growth as we get going because we are taking 25% of a bigger population. Let me show you that one. So again, see how their growth rates are not the same, right? These are the changes in Y's. 1 year, the change in Y was this much. The next year, the change in Y was that much. So that is really our fundamental understanding of how exponential growth happens. We keep what we started with, and as soon as we gain it, we don't lose it. The amount that we gain the following year is based off of what was there prior. So what we're going to move on now is a little less kind of conceptual understanding and kind of getting some quote unquote more mathy understanding. So the general formula for exponential growth looks like this. And we really need to see it more than just an equation. We need to see it as a bunch of parts. So first thing that's important, as we saw with this Austin, Texas thing, is the amount that started, or our initial amount. There's a lot of different names for it. I'll call it the starting amount or the initial amount. But we saw that however much you start with makes a huge difference on how much you grow by, right? If we think about this, if we had started with less people in Austin, Texas, like if we just started with this much, the amount of growth, like a quarter of it, would have been a lot less. So our population would have looked a lot different had we had started with different amount of people. So that's why that A value is going to be critical to our understanding of the formula. So how much did you start by? Now I want you to see the parentheses in two ways. You need to see it first of all as one number, right? So we're going to see A is being multiplied by this number in parentheses. This number in parentheses is called the growth factor. And the way that I remember the difference between the word growth factor and growth rate is a factor is a number that's part of a multiplication problem. So this entire parenthesis is being multiplied by A, and just think of it as one number. So that's why it's called the growth factor. This little value of R is called the growth rate. And we'll see that a little bit as we work through the examples, like what's the difference. The growth rate is the change in percent from the year before, like so in our example, 25%. And then T is going to be the amount of time that has passed. And I want us to think of our growth rate and our growth factor in two kind of, like I said, different ways. Let's come back up to this example here. So our population started, and I don't care what that is, just write this equation. Our population started with 100,000 people. So our A value is 100,000. Now, when we think about this growth factor, the amount that it was changing by, the rate, was 25%. So when you put it into the equation, you always have to put it in as a decimal. Now, this 1 is always part of the formula. And the way I want you to think about that is the 1 is representing keeping 100% of what was there, right? That red rectangle was always there. So we always have to keep 100% of what we had. The plus sign to me means we're adding or growing by some amount. And then this 25% of that, I'll just leave it 25%. So we're keeping 100% of what was there, right? So we kept 100% of what was there, and then we grew by 25%. We kept 100% of what was there, and then we grew by 25%. And now the T is just how many times are we going to do that? Are we going to do it for 1 year? Are we going to do it for 2 years? Are we going to do it for 3 years? So if I label this one would have been, okay, I started with all 100,000 people. I kept all of them, and I grew by 25% for 1 year. If I label this box, we could represent this as saying, well, I started with all 100,000 people. I kept them every time, kept 100% of them, and I grew by 25%. But this time I did it twice. Right? So on and so forth. And that's why I want you to see this equation in two different ways. Notice how I said that. I said I started with this much. I already wrote that, sorry. I kept 100% of what was there, and then I grew by this much. Super informative when we have it in that form, right? Now there's another form that I want you to be able to see it as, though, so I'm going to rewrite it as y equals 100,000, because we have to keep those people. They're not moving away. But this time we could just write it as 1.025 to the t. Now, why would we want to see it like that? Well, the same type of narrative is there. We need to keep all of what we started with. But rather than keeping 100% and growing by 25, sorry, I have too many zeros in there. That's my fault. 1.25. You could also interpret this as growing by 125%. Right? Now, I want you to see the difference between keeping 100% of what you had and then just getting 25% more, or saying I'm just going to take this and take 125% of that, right? The 100% is from before, the 25% is added. So you really want to make sure you can see it in both ways. Let's jump into an example. The average price of a movie theater ticket in 2005 was $6.50, and it's been increasing by 6% per year. So we want to be able to write this as an equation in terms of the number of years since 2005. Okay, so our price is a function of the number of years. And the way that we're going to write this is, how much should I start with? Well, the $6.50 price is always going to be there. We're going to keep that every time, but we're going to grow by 6%. And we're going to do that as many number of times as it's been years since 2005. So if we used that formula, what is the price of the ticket in 2014? Well, we'd have to say, okay, we are going to take 106% of that for 9 years, because if it started at 2005 and I went to 2014, it's grown this many times. And it doesn't really matter what way you want to see it. I prefer this way at times because it's a little bit easier. I've kept the 100% and added 6%. I'm struggling with my zeros, sorry. And I've added 6% for 9 years. So if you type that into your calculator, and that's how you'll have to do these. There's no real way to calculate a lot of this without a calculator. Make sure you're typing exactly what you see, like using parentheses. I did that for 9 years. Tickets are going to cost $10.98. We will get into solving these. According to this model, when will the cost of the movie tickets reach $25? So I know how to model the ticket. We already wrote this formula. I just don't know how many years it's been in order for that output, or in other words, that answer, to be $25. Now, we will have some ways that we can do it algebraically. We'll get there later in the unit. But for right now, the only way that we're going to be able to do this type of problem is graphically. So we type in the equation that models the cost of the ticket. I have to use x. I'm going to set my window. If x's are measuring years, I don't need to use negative years. I don't know how many years it's going to take, so I'm just going to say, let's start at 20 years. The y values are measuring ticket price, and I know it started at $6.50, so it can't get lower. I'm just going to make my window a little bit easier to read, so I'm going to start at $5. And if I need to see when it gets to $25, let's just round up to $30, and let's just have the y-axis count by $5 increments. I also need to graph the line 25. And then my calculator is a little bit different than yours, right? But you know how to do second calc, find that intersection point, first curve, blah, 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 blah. Like I said, mine's a little bit different than yours, so I got to do it a little bit different. But we'd find that point of intersection, and that's the only way that we can actually solve these. So it looks like on this one, I get, what does it say? X is 3.89, which I think I have a mistake. Yep, sorry, I typed my thing in, let's just say 2 to the power of x. My bad. That looks a lot better. I can see this point of intersection doesn't look good. I need more x values, right? I need to go further to the right. Let's make it 50 years. So first of all, we see that classic exponential shape, right? So as I get closer, as time progresses, the ticket price is getting closer to 25, and that's where you guys are doing the second calc, intersect, blah, blah, blah. My calculator's a little bit nicer right now. When you do it, I already have it prepared, but I'll kind of do it real quick here. Left bound, right bound. And when you do it on your calculator, looks like we get 22.97 or something close. If my calculator didn't do the exact point of intersection, yours will. But again, we all know how to do points of intersection on the calculator. And I didn't mean to make you nervous on that last one. The exact point of intersection for the t time was 23.1182, just to make sure. I didn't mean to be bad at my calculator. The last part of today is a special type of interest that we're going to be looking at, which is compound interest, just because it has to deal with money. So I've written kind of some definitions here for you to either write down, pause the video and copy, or go ahead and just read through. But simple interest, meaning we're going to pay you interest on how much you gave us. If you give me $100, I'll pay you interest on that $100, but I'm not going to pay you for the money that I've given you, right? So like in simple interest, if I start with $100 in my bank account and you pay me 5%, next year you've paid me 5% of $100, which is $105 in my bank account then. But principal interest is saying you only invested this much, so I'm only going to pay you 5% of what you invested. So next year, you're going to have $110 because you earn 5% of your original investment. Compared to compound interest, and in compound interest, what happens is they pay you for whatever you currently have. So the first years would look similar because I still earn 5%, but now I'm earning 5% of what I already had. So now I'm going to gain like $5.25. So we can see that there's a little bit of an advantage to this one because they're paying you for what they already paid you. And then I have a definition of what the word compounding means. Compounding is how many times are they going to pay you, right? So if I'm going to say I'm going to pay you 5% interest, am I just going to pay you once at the end of the year? Am I going to take that 5% and give you half in June and give you the other 2.5% in December? Am I going to take that and just split it up over 12 equal payments? So that's what the word compounding means, right? So what I want to get to just with this one right away is kind of just the general formula, and then we'll work through like what does it mean. The general formula for compound interest is going to look similar. It's going to be y equals a times 1 plus r over n to the n times t. Now, what is everything going to mean? Well, a is still our principal amount, how much we started with. R is still that growth rate, but here we're specifying that the growth rate is expressed over 1 year, because n is going to be the number of compounds, meaning that growth rate that they're going to give you, that 5%, how many times are they going to split it up over the year? So therefore then, t is still time, because if I take 5%, let's say I'm going to split it up twice. I'll pay you twice a year. That means this would happen twice for every year. And to be more specific, this is the number of years. So let's just jump into like an example right here. So it says we're going to invest $8,200 into an account that's going to guarantee to pay us this much percent over the entire year. However, they're going to split that percentage up based on how they're going to compound it. So first of all, if we were going to compound it annually for 5 years, let's write that formula. Well, we're still going to start with $8,200. We're always going to keep 100% of what's in our account, and we're going to grow by a certain percentage, but we're not earning 3.65% every time. That's what we get after 1 year. So they're going to take that 3.65%, which is 0.0365 as a decimal. And in this case, annually, that means they're only going to pay us that percentage once. So this is going to happen one time for every 5 years. You'll have to type that into your calculator. I already have it prepared. It comes out to be $9,809.81. So we definitely made money, right? Now, what would happen if they compounded semi-annually, meaning twice a year? So this formula will start with $8,200. Every time we get paid, we're going to keep 100% of what we have. But now that 3.065% is going to be split up into 2 payments. So in other words, I'm going to be paid, right? I'm going to gain something twice every year. And this example wants us to do it for 5 years. So typing this one into your calculator, you'll get this output value, 9825.58. Now, if you're noticing on your calculator that you're writing this, but you're not getting that, it's just usually how you're using parentheses. So if you're having difficulties getting these outputs on your calculator, put the exponents in an extra set of parentheses, put this in an extra set of parentheses. And if you're not already, you should be using that fraction button, right? And with that fraction button, just makes formatting so much easier. Alpha F1 pull up the fraction bar, 0.0365 divided by 2. I need to raise that to the 2 times 5 power. All right. It is money. Our money system only goes to the second decimal, so we always round to 2 decimals. Let's do another one. Go ahead and try to get ahead of me on this one. So with this one, we're always starting with what we invested. We're going to keep 100% of it, and we're going to gain something. Now, in this scenario, that 3.65% they've told us they're going to pay us, they're actually going to split it up quarterly now. So there's 4 quarters. So in other words, I'm going to be paid 4 times for each of those 5 years. We're going to see on this one, I believe the output value is 9833, right? I'll kind of skip around a little bit. Let's do daily. So if we get paid every day, that means there's 365 days in the average year, let's say. So that's how much we're investing. We'll always keep 100% of it, but that 3.65% we're going to earn total is going to take us 365 days to earn it, because they're going to split it up into that many payments. And then, which means we'll be paid 365 times for each of those 5 years. This one comes out to be this value. Now, hourly, I kind of did the math for us. There's this many hours in the year. So all I'm going to do, I'm just going to save some time. We'll copy and paste this and just change out the values that we need to change, right? Now, those payments are going to happen much more frequently. They're going to be paid every hour. So it's like we're going to be taking that 3.5% or 3.65% and splitting it up, which means we'll get paid that many times for each of those 5 years. And then this output value, 9841.75. So first of all, there's 2 things going on here. Just the nuts and bolts of the formula, the interpretation of, hey, that percentage is being split up into this payments. So for every 1 year, I'm going to get paid that many times. But then I also want you to copy this part down here, which you'll see on top of the screen here. What are we supposed to notice? Like, why do we care about compound interest? Why is it different? Why are there so many different combinations of it? Well, just notice the money got bigger, right? If I only got paid once a year, if I got paid twice a year, if I got paid a ton of times a year, right? Now just notice how that value is going up as the number of compounds increases, all right? So that's what I really want you to write up here. The total money earned is increasing as the frequency of compounding increases. And of course, I'm assuming we're always talking about that same percentage rate. And the idea there is you have more opportunities to earn money. They're going to pay you a percentage of what you have in your account. So if they're paying me more frequently, they're paying me a percentage that's always a little bit more, right? Because every hour I'm getting a little bit more in my account. So every hour they have to pay me a little bit more. Whereas here, my account isn't changing. They only pay me at the end of the year. Here, my account's only changed twice. So that first time they pay me, it's no different. The second time I got paid a little bit more. They paid me for the money that they already paid me. So that's the general idea there. This one here, just a total quick another example. You could pause the video and pound through it, or you could just not do it. It's up to you. But just summarizing our work for today. So we invest this much money at that much interest compounded quarterly. We need to write a function for the amount of money as a function of time. So the amount in my bank account, if I want to know that, I have to input some value of time. So I've started with $100. I'm always going to keep that much. I'm going to add some to it. They've told me they're going to give me 5.1%, but they're not going to give that to me in just one installment per se. They're going to split that up quarterly, which is 4 times. So for every year, I'll be paid 4 times. So what is the compound amount after 8 years? So in other words, how much money do we have after 8 years? So the amount in our bank after 8 years, like when you're showing your work, you obviously want to plug in the numbers. I would never really simplify the fraction. I would just leave it as is, but we can plug that in as an 8. And when we do that, again, on your calculator, I've already prepared this just for speed. You should get this value. When will it reach that amount? So in other words, we don't know what time is, right? So we're not inputting a time value. We're wondering when would the output of our equation or our function be 10,000. So in other words, we have this equation and we're still being paid 4 times, but but we don't know how many years it would take to get to $10,000. And as a reminder, this is the one where we have to do it graphically. So we'll first write our exponential equation, 3,500. 1 plus, always recommend using the fraction. We're gaining 5.1% compounded quarterly. So then we're going to be paid 4 times, to the power of 4 for every year. And I want to know when this is going to be $10,000. Setting my window up, X in this case is time. It's the number of years. I have no idea how many years it's going to take, but I know it's not negative. For the sake of the scale, I'll probably just count by 5. Y values is how much money we have. If we started with $3,500, let's just start a little bit lower than that so we can see something on our y-axis. Now we're trying to get to 10,000, so I'm just going to round up to 15,000. How much do I want to count by on my y-axis? Probably like 10,000, or sorry, maybe 1,000. Doesn't really matter. See how that looks. So first of all, we can see 2 things, right? You can see that classic exponential shape. And then we can also see the linear shape in red. So where do they touch? We'll second calculate the intersection. And again, yours is a little bit different than my calculator, but I'm just kind of making sure you know the process. Where do I think they, oops, I just missed it. I forgot mine's a little bit different. So left, right. So it looks like the number is 20.7157. So T equals 20.7157 years. All right, so that's your notes on exponential growth. There is a ton here, super important. The good thing is tomorrow is just exponential decay. Literally the same thing, but instead of, if you can't already guess it, instead of starting with 100% of what you had and gaining some percentage, you're just going to be losing a percentage. So there you go.